Hey everybody. Today we're talking about the Poisson distribution, which models the number of occurrences of a random event over a set period of time. The events are assumed to be independent from one another and to occur at a constant average rate. In other words, they're assumed to occur according to a Poisson process. I think this is all clearer when we mention a couple of examples, so here's three. Poisson distribution might model the number of calls to a customer service line in a 10-minute interval, the number of accidents along a busy stretch of road in an hour, or the number of mistakes made by an amateur typist in a 100-word paragraph. In each case, the outcome could be any non-negative integer. The probability mass function for a random variable with a Poisson distribution is given by lambda to the x times e to the negative lambda over x factorial, where lambda is a parameter for this distribution called the rate parameter that represents the average number of occurrences per unit interval. The support of this random variable is going to be all the positive integers, or rather all the non-negative integers, 0, 1, 2, 3, etc. For instance, if we have a rate parameter of lambda equals 2.5, then the distribution of the Poisson distribution with lambda equals 2.5 looks like this. While any positive integer, or at least non-negative integer, is a possible outcome here, values larger than about 8 are extremely unlikely in this case. Let's do an example. Around dinner time, orders at a pizza shop come in at an average rate of 4 every 10 minutes. What's the probability that there will be exactly 5 orders in a 10-minute period, fewer than 5, or at least 5? So we'll do each one of those 3 probabilities. We are going to use a 10-minute interval as sort of our standard time period here, and so the random variable x that counts the number of occurrences in that time period is going to have a Poisson distribution with parameter 4. So the probability mass function is 4 to the x e to the negative 4 over x factorial, and we can compute the probability that x equals 5 just by plugging 5 into that probability mass function. When we do the arithmetic, we get about 15.6%. So the probability that exactly 5 orders come in a 10-minute period is 15.6% approximately. Similarly, to get the probability that x is less than 5, we're going to add up the probabilities for all the integers less than 5, starting with 0. When we do that, we get about 62.9%, and the probability that x is greater than or equal to 5 is going to be complementary to that, so we'll do 1 minus the probability that it's less than 5. We get about 37.1%. It's often the case that we need to compute probabilities for intervals of different lengths than the one for which we know lambda. So like in that last example, we knew that lambda was 4 when we were talking about a 10-minute period of time. But we might want to compute the number of orders that come in an hour or a minute or any other period of time. So this fact helps us address that. Suppose we have a random variable x that models the number of occurrences in an interval of length L. So it has a Poisson distribution with parameter lambda. Then the number of occurrences that occur on a different interval length, say CL, has the Poisson distribution with parameter c times lambda. So if you scale the length of the interval by c, you also scale the average number of occurrences by that same factor. Going back to that pizza place example where we have an average of 4 calls every 10 minutes, 4 orders every 10 minutes, let's try and find the probability that there will be exactly 25 orders in a 60-minute period. So this is a good place to pause the video, try this on your own before seeing my solution. If we expect 4 orders every 10 minutes, then we expect 24 orders every hour because 6 times 10 is 60, so we need 6 10-minute periods to get to an hour. So 6 times 4, 24. And then we're going to compute the probability of getting exactly 25 orders in that hour just by doing the probability that x equals 25 in this Poisson distribution. Plugging in lambda equals 24 and x equals 25, simplifying, we get about 7.8%. Many problems and proofs in using the Poisson distribution rely on the Maclaurin series expansion for the exponential function. It's sometimes called the fundamental identity of this distribution. And the Maclaurin series expansion for e to the t is given by the sum from k equals 0 to infinity t to the k over k factorial. And if you expand that out, that's 1 plus t plus 1 over 2 factorial times t squared plus 1 over 3 factorial times t cubed, etc. So for instance, we can use that property to show that the probability mass function that we're given is actually a legitimate probability mass function. In other words, that all the possible probabilities add up to 1. So just putting the summation in front of our probability mass function and summing up over the support, we see that we have one factor here that we can pull out of the summation. That's the one that doesn't have any x's in it. So we pull out the e to the negative lambda. Once we've done that, the summation that we have now is just that Maclaurin series that I showed on that previous slide, just with lambda instead of t. And so that whole summation simplifies to e to the lambda. We're left with e to the negative lambda times e to the lambda, which of course is 1. So this does verify that necessary property of any legitimate probability mass function. Let's do another example. A bookstore keeps 8 copies of a popular cookbook in stock. Suppose the number of sales in a day follows a Poisson distribution with mean 7. What's the probability that the store can't meet the demand on a given day? How many copies should they keep in stock so that the probability of turning a customer away is less than 10%? In this case, we are going to let x model the number of sales that we have in that day, and so x is going to have a Poisson distribution with parameter lambda equals 7. On average, 7 sales in a day. We need to know the probability that x is greater than 8. And we'll do that using the rule of complements, 1 minus the probability that x is less than or equal to 8. We then compute the probability that x is equal to 0, 1, 2, 3, 4, 5, 6, 7, and 8. Add all those up and subtract from 1. We get about 27.1%. So from the perspective of the store, they're not meeting demand on 27-ish% of days, so maybe this isn't ideal. We'd like to know how many copies they should keep in stock in order to have less than a 10% chance of turning away customers on a given day. So we need to find the x such that the probability that the random variable is less than or equal to x is greater than or equal to 90%. And we can just do that by plugging some values in just like we did a moment ago with 8. So we'll do it for 8, 9, 10 until we finally get over 90%. It turns out that the probability that x is less than or equal to 9 is 83%. The probability that x is less than or equal to 10 is 90.1%. And again, those computations are done exactly in the same way as we did the probability that x is less than or equal to 8. Overall, we conclude that the store needs to stock 10 copies of the cookbook to meet demand 90% of the time. Both the expected value and variance of a random variable with a Poisson distribution are just equal to the rate parameter lambda, and therefore the standard deviation, the square root of the variance, is the square root of lambda. And the fact that the mean, the expected value, is equal to lambda justifies the description I used earlier that lambda is the average or expected number of occurrences per unit interval. Now, I'm not going to prove these facts right now. They're typically proved using the moment generating function, which we haven't gotten to yet in the normal knowledge probability course, but that's coming up really soon, so you'll get to that. Let's do one more example. A factory producing cardboard boxes averages 2 flawed boxes per hour. Find the mean and variance of the number of flawed boxes in an 8-hour shift, and then compute the probability that the factory produces between 12 and 20 flawed boxes, including 12 and including 20, in that 8-hour shift. So, if there's an average of 2 flaws per hour, that corresponds to an average of 16 flaws in an 8-hour shift. So I'm doing just 8 times 2 to get that 16. And so since lambda is 16, that's both the expected value and the variance. The standard deviation for a random variable with this distribution, representing the number of flawed boxes in a day, is going to be 4. If we look at this random variable with that parameter lambda equals 16, we can compute the probability that x is between 12 and 20 inclusive just by computing all the individual probabilities from x equals 12 up to 20 and adding all those up. And we get about 74.1%. Now, that's a real pain in the butt to do all of that arithmetic by hand or even with a calculator, and so typically these calculations are done using technology. And any self-respecting piece of computational software is going to have built-in functions for both the probability mass function and cumulative distribution function for a random variable with a Poisson distribution. I use R, where the commands are dpois and ppois respectively for the PMF and CDF. So for instance, using the distribution from that last example, the Poisson distribution with lambda equals 16, the probability of 15 flawed boxes in a shift is going to be given by d Poisson 15, 16, which is about 9.9%. And the probability that we computed in that example, that x is between 12 and 20 inclusive, is p Poisson 20, 16 minus p Poisson 11, 16. So by doing the p Poisson of 20, 16, we're getting the probability of being less than or equal to 20. Then we're taking away the probability of being less than or equal to 11 when we subtract off that other p Poisson. We get 74.1% just as before. Last comment before I wrap up this video is that the Poisson distribution is closely related to several other distributions that you'll run into when you're studying probability. And so when you run into a word problem, you want to make sure you don't get it confused with some of these others. First of all is the binomial distribution, which of course models the number of occurrences of an event that can have exactly two different outcomes, success and failure, over a finite number of trials where the event always has a fixed probability of occurring in each trial. So in a situation like that, if you have, say, n trials, the outcome for the binomial random variable can only be between 0 and n. By contrast, when we're talking about a random variable with a Poisson distribution, there aren't individual trials for the random variable, and there's no upper bound in theory to the number of occurrences that could occur. The second distribution I want to mention here is the gamma distribution, which models the waiting time until you get a given number of successes when you have a Poisson process. So you might be waiting on the fifth flawed box there. Now, we are still having the same situation where we have a Poisson process where occurrences are where we're waiting on occurrences. The Poisson process, the Poisson distribution counts the number of occurrences that happen, whereas the gamma distribution looks at the waiting time until a specified occurrence. One tip-off that you're in one and not the other is that a gamma distribution is going to be referring to a continuous random variable, waiting time, while a Poisson distribution is going to be a discrete distribution. So there we're counting, and we can only get values like 0, 1, 2, 3, 4, 5.